In this chapter, we focus on web crawler design, an interesting and classic system design interview question. A web crawler is known as a robot or spider. It is widely used by search engines to discover new or updated content on the web. Content can be a web page, an image, a video, a PDF file. Web crawler starts by collecting a few web pages and then follows links on those pages to collect new content. Figure shows a visual example of the crawl process. A crawler is used for many purposes. Search engine indexing. This is the most common use case. A crawler collects web pages to create a local index for search engines. For example, Googlebot is the web crawler behind Google search engine. Web archiving. This is the process of collecting information from the web to preserve data for future use. Many national libraries run crawlers to archive websites. US Library and EU Web Archive. The explosive growth of web presents an unprecedented opportunity for data mining. Web mining helps to discover useful knowledge from the internet. Top financial firms use crawlers to download shareholder meetings and annual reports to learn company initiatives. The crawlers help to monitor copyright and trademark infringements over the internet. Digimark utilizes crawlers to discover pirated works and reports. Complexity of developing a web crawler depends on scale we intend to support. It could be either a small project which takes only a few hours to complete, or a gigantic project that requires continuous improvement from a dedicated engineering team. Thus, we will explore the scale and features to support below. Understand the problem. Given a set of URLs, download all the web pages addressed by the URLs, extract URLs from these web pages, add new URLs to the list of URLs to be downloaded. Does a web crawler work truly as simple as this basic algorithm? Not exactly. Designing a vastly scalable web crawler is an extremely complex task. It is unlikely for anyone to design a massive web crawler within the interview duration. Before jumping into the design, we ask questions to understand the requirements and establish design scope. What is the main purpose of the crawler? Is it used for search engine indexing or something else? How many web pages does the web crawler collect per month? What content types are included? HTML only or other content types such as PDFs and images as well? Shall we consider newly added or edited web pages? Do we need to store HTML pages crawled from the web? How do we handle web pages with duplicate content? Above are some of the sample questions that you can ask your interviewer. It is important to understand and the requirements and clarify ambiguities. Even if you are asked to design a straightforward product like a web crawler, you and your interviewer might not have the same assumptions. Beside functionalities to clarify with your interviewer, it is also important to note down the following characteristics of a good web crawler. The web is very large. There are billions of web pages out there. Web crawling should be extremely efficient using parallelization. The web is full of traps. Bad HTML, unresponsive servers, crashes are all common. Crawlers must handle all those edge cases. The crawler should not make too many requests to a website within a short time interval. The system is flexible so that minimal changes are needed to support new. content types. For example, if we want to crawl image files in the future, we should not need to redesign the entire system. The following estimations are based on many assumptions, and it is important to communicate with the interviewer to be on the same page. Once the requirements are clear, we move on to the high level design. Inspired by previous studies on web crawling, we propose a high level design as shown in the figure. Seed URLs, URL frontier, HTML downloader, DNS resolver, content parser, content scene, content storage, link extractor, URL filter, URL scene, URL storage. First, we explore each design component to understand their functionalities. A web crawler uses SID URLs as a starting point for the crawl process. Example: to crawl all web pages from a university's website, an intuitive way to select seed URLs is to use the university's domain name. To crawl the entire web, we need to be creative in selecting seed URLs. A good seed URL serves as a good starting point that a crawler can utilize to traverse as many links as possible. The general strategy is to divide the entire URL space into smaller ones. The first proposed approach is based on locality, as different countries may have different popular websites. Another way is to choose seed URLs based on topics. We can divide URL space into shopping, sports, healthcare. Seed URL selection is an open ended question. You are not expected to give the perfect answer. Most modern web crawlers split the crawl state into two: to be downloaded and already downloaded. The component that stores URLs to be downloaded is called the URL frontier. You can refer to this as a first in first out queue. For detailed information about the URL frontier, refer to the deep dive. The HTML downloader downloads web pages from the internet. Those URLs are provided by the URL frontier. To download a web page, a URL must be translated into an IP address. The HTML downloader calls the DNS resolver to get the corresponding IP address from the URL. After a web page is downloaded, it must be parsed and validated before malformed web pages could provoke problems and waste storage space. Implementing a content parser in a crawl server will slow down the crawling process. Thus, the content parser is a separate component. Online research reveals that 30% of the web pages are duplicate contents, which may cause the same content to be stored multiple times. We've introduced content scene data structure to eliminate data redundancy and shorten processing time. It helps to detect new content previously stored in the system. To compare two HTML docs, we can compare them character by character. However, this method is slow and time consuming, especially when billions of web pages are involved. An efficient way to accomplish this task is to compare the hash values of the two web pages. It is a storage system for storing HTML content. The choice of storage system depends on factors such as data type, data size, access frequency, lifespan. Both disk and memory are used. Most of the content is stored on disk because the dataset is too big to fit in memory. Popular content is kept in memory to reduce latency. URL extractor parses and extracts links from HTML pages. Figure shows an example of link extraction process. Relative paths are converted to absolute URLs by adding the prefix. URL filter excludes certain content types, file extensions, error links, URLs in blacklisted sites. URL scene is a data structure that keeps track of URLs that are visited before or already in the frontier. Bloom filter and hash table are common techniques to implement the URL scene. We will not cover the detailed implementation. त्याच्यामध्ये लेफ्ट टू राईट कसं करायचं? Customization, public category, thumbnail. Yes, like bedroom, automatic chapter, allow tags, language, option verification, training, yes, command, stream, customer, Bloom filter and hash table are common techniques to implement URL stream component. We will not cover the detailed implementation of the Bloom filter and hash table here. URL storage stores the visited URLs. We have discussed every system component. We put them together to explain the workflow. To better explain the workflow step by step, sequence numbers are added in the design diagram. Add seed URLs to the URL frontier. HTML downloader fetches a list of URLs from URL frontier. The downloader gets IP addresses of URLs from DNS and starts downloading. Content parser parses the pages and checks if pages are malformed. After content is parsed and validated, it is passed to the content scene component. Content scene checks if a HTML page is already in the storage. If it is in the storage, this means that the same content in a different URL has already been processed. Link extractor extracts links from HTML pages. Extracted links are passed to the URL filter. After links are filtered, they are passed to the URL scene component. Extracted links are passed to the URL filter. URL string component checks if a URL is already in the storage. If a URL has not been processed before it is added to the URL frontier. Up till now, we have discussed the high level design. We will discuss the most important building components and techniques. DFS versus BFS, URL frontier, HTML downloader, robustness, extensibility. You can think of the web as a directed graph where web pages serve as node and hyperlinks as edges. The crawl process can be seen as traversing a directed graph from one web page to others. Two common graph traversal algorithms are DFS and BFS. However, DFS is usually not a good choice because the depth of the DFS can be very deep. BFS is used by web crawlers and is implemented by a first in first out queue. In FIFO, URLs are dequeued in the order they are enqueued. However, this implementation has two problems. Most links from the same web page are linked back to the same host. All links in the Wikipedia are internal links, making the crawler busy processing URLs from the same bot. When the crawler tries to download web pages in parallel, Wikipedia servers will be flooded with requests. This is considered impolite. Standard BFS does not take the priority of URL into consideration. The web is large and not every page has the same level of quality and importance. So we may want to prioritize URLs according to their page ranks. URL Frontier helps to address these problems. A URL is the data structure that stores URLs to be downloaded. The URL is an important component to ensure politeness, prioritization, and freshness. A few noteworthy papers on URL Frontier are mentioned in the reference material. Generally, a web crawler should avoid sending too many requests to the same hosting server within a short period. Sending too many requests is considered as impolite or even treated as denial of service attack. For example, without any constraint, the crawler can send thousands of requests every second to the same website. The general idea of enforcing politeness is to download one page at a time from the same host. A delay can be added between two download tasks. The politeness constraint is implemented by maintaining a mapping from website hostnames to download worker threads. Each downloader thread has a separate FIFO queue and only downloads URLs obtained from that queue. A random post from a discussion. FIFO queues. Each queue contains URLs from the same host. Each worker thread is mapped to a FIFO queue, and it only downloads URLs from that queue. The queue selection logic is done by the queue selector. A random post from the discussion forum about Apple products carries very different weight than posts on the Apple homepage. Even though both have the Apple keyword, it is sensible for a crawler to crawl the Apple homepage first. We prioritize URLs based on the usefulness. It takes URLs as inputs and computes the priorities. Each queue has an assigned priority. Queues with high priority are selected with higher probability. Randomly choose a queue with a bias towards queues with a higher priority. It presents the URL frontier design and it contains two modules: manage prioritization and manage politeness. Web pages are being constantly added, deleted, and edited. A web crawler must periodically crawl downloaded pages to keep our dataset fresh. Recrawl all the URLs is time consuming and resource intensive. Few strategies to optimize freshness are listed as follows. In real world crawl for search engines, the number of URLs in the frontier could be 100. Putting everything in memory is neither durable nor scalable. Keeping everything in the disk is undesirable, neither because the disk is slow and it can be easily become a bottleneck for the cron. We adopted a hybrid approach. The majority of the URLs are stored on disk, so the storage space is not a problem. To reduce the cost of reading from the disk and writing to the disk, we maintain buffers in memory for NQ and DQ operations. Data in the buffer is periodically written to the disk. The HTML downloader downloads web pages from the internet using HTTP protocol. Before discussing the HTML downloader, we'll look at the robots exclusion protocol first. Robots exclusion protocol is a standard used by websites to communicate with crawlers. It specifies what pages crawlers are allowed to download. Before attempting to crawl a website, a crawler should check its corresponding robots.txt file and follow its rules. To avoid repeat downloads of robots.txt files, we cache the results of the file. The file is downloaded and saved to cache periodically. Here is a piece of robots.txt file taken from Amazon robots.txt. Some of the directories like Creator Hub are disallowed for Googlebot. Besides robots, performance optimization is another example. To achieve high performance, crawl jobs are distributed into multiple servers, and each server runs multiple threads. The URL space is partitioned into smaller pieces, so each downloader is responsible for a subset of URLs. Figures are an example of distributed crawl. DNS resolver is a bottleneck for crawlers because DNS requests might take time due to the synchronous nature of many DNS interfaces. DNS response time ranges from 10 to 200. Once a request to DNS is carried out by a crash crawler thread, other threads are blocked until the first request is completed. Maintaining our DNS cache to avoid calling DNS frequency is an effective technique for speed optimization. Our DNS cache keeps the domain name to IP address mapping and is updated periodically by cron jobs. Distribute crawl servers geographically. When crawl servers are closer to website host, some web servers respond slowly or may not respond at all. To avoid long wait time, a maximal wait time is specified. If a host does not respond within a predefined time, the crawler will stop the job and crawl some other pages. This helps to distribute load amongst downloaders. A new downloader server can be added or removed using consistent hashing. To guard against failures, crawl states and data are written to a storage system. Disrupted crawl can be restarted easily by loading saved states and data. Errors are inevitable and common in a large scale system. The crawler must handle exceptions gracefully without crashing the system. As almost every system evolves, one of the design goals is to make the system flexible enough to support new content types. The crawler can be extended by plugging in new modules to add how to add new modules. This section discusses the detection and prevention of redundant and meaningless content. As discussed previously, nearly 30% of the web pages are duplicates. Hashes to help detect duplication. A spider trap is a web page that causes a crawler in an infinite loop. But an infinite deep directory structure is as follows. Such spider traps can be avoided by setting a maximal length for URLs. However, no one-size-fits-all solution exists to detect spider traps. Server-side rendering. Numerous websites use scripts like JavaScript, Ajax to generate links on the fly. If we download and parse web pages directly, we will not be able to retrieve dynamically generated links. With finite storage capacity and crawl resources, an anti-spam component is beneficial in filtering. For large-scale crawlers, hundreds or even thousands of servers are needed to perform download tasks. Collecting and analyzing data are important parts of any system because data is key ingredient for fine-tuning. Now give yourself a pat on the back and enjoy. आता जाऊन तर आम्ही वेट लिफ्टिंग करू.